Welcome back to this segment on materials. As you know, we've been working on Chapter 2, and this will be the third and the last segment discussing material properties in Chapter 2. The main idea is that we have a variety of materials in our disposal that enable us to meet design requirements. So we want to be familiar with the types of materials, the terminology, that is used in material selection, and then we will develop some indices that make it easier to select materials for particular design applications. So as you know, there are classes or families of materials. For example, we know metals. That's a big family of materials. And metals are a variety of alloys. They depend on the base metal, and then the additions improve the base metal properties when it's alloyed with this. The main groups of alloys within the metal family, they're dominated obviously by steel. And steel, the base is iron, and then you have additional elements that control the properties of the steel. The main element that is used is carbon, and the percentage is really very small. And the different varieties of steels vary from cast iron to stainless steel to a group of steels that is called martensitic steels to ferritic steel. So all of these names that you will see when you review in the book, they relate to the structure or the microstructure within the steel family. Also, when we speak of alloy steels, it means that we go beyond carbon, because the carbon controls the properties to a certain extent, but to give the steel high temperature strength, for example, we need to alloy it with elements like molybdenum, vanadium, tungsten, chromium, and so forth. So that's kind of the main dominant group of alloys within the metal family. Second to that in utilization is aluminum, and aluminum we have a number of alloys within the aluminum system. And then you get into other base alloy systems that are based on nickel, that are based on copper, and other variety of elements like titanium, for example, is also used extensively. So that's one family. And then we move on to another family. Another family is called ceramics. And in ceramics, the structure is based on a bonded, very highly bonded atomic structure. It doesn't have, it's very, very strong bonding, but it doesn't have flexibility to include plastic deformation when it is highly or severely deformed. So this group of materials within this family of ceramics, they usually compose of two or more elements. For example, silicon carbide, so you have silicon and carbon, and they bond it together with a very strong electronic covalent bond. Usually for ceramics, the strength is high and the elastic modulus is also very high, but they don't have very good fracture resistance. So that's another group. A third group of materials, a family of materials, is called composites. And in composites, we can have distinct members of different families and mix them together. For example, we could have wires made of tungsten or steel, and then embed that in a moldable plastic and make a composite. So it has a combination of the properties of these two different materials come from two different families. So a composite is kind of like combination of these two families that I talked about. But we have other families of materials that are grouped together. So I'm going to review the different kinds of families of materials, and we'll discuss their general properties that are useful in design, general characteristics, and then it will take a little bit of reading on your part to understand more about how to select a particular material from each group of materials within the family. So as you can see here, the metal family is essentially made of the elements that I discussed, and these are the most significant elements that designate the families of the family within the or the class of metals within the family, going from aluminum to copper to lead, magnesium, nickel, carbon, stainless steel, tin, titanium, tungsten, lead, and zinc. And beyond that, we would have to look at a different family, as I mentioned. The second family is the ceramics. And the ceramics, there are some names used in the common names like alumina, but the alumina, if you look at it, is aluminum oxide, basically. Aluminum nitride, which is aluminum AlN, boron carbide, B4C, silicon carbide, SiC, and so forth. So that's a group of materials or class of materials within the family of ceramics. We also have what's called non-technical ceramics, which are made from bricks, concrete, and stone. In mechanical engineering applications, usually we don't use this group of materials. Usually, for civil applications, they are very useful. We also have glasses, and glasses are, as you can see here, the classes of materials within glasses are glass ceramics, silica glass, borosilicate, soda lime glass as examples. Next is the family of polymers. And the polymers, we have two different groups within the polymers. The first one is called thermoplastic, and the second one is called thermoset. So what are the differences between thermoplastics and thermoset? Here I'm going to go back and then discuss the difference between thermoplastics and thermosets. Thermoplastics is a material where we can reuse it many times. So it's moldable, and when you heat it up, it softens, like some of the plastics that you know, and you can remold it. And that's obviously very nice for recycling and protection of the environment. The other group is called thermoset, and that is once the polymerization process ends and finishes, then you cannot remold it again. So it is set already and is very difficult to change. So you have to shred it, and you have to redo the polymerization process on a chemical basis to recover the elements. So there's an issue here in the area of recycling. So these are the two different groups. So if you look at some of the common names, for example, thermoplastic, you have the ABS group, and these are the properties in table 2.2. This is the ultimate strength, 2 to 8 kilopascal. This is the elastic modulus, 0.1 to 0.37 mega psi. And these are what I would like to point out, the processing here routes that you have available is indicated in this column, where C is coatings, L is laminate, R is resin, and so forth. So you just have to look at the different available forms for the thermoplastic. So you might be familiar with some of the names here, like nylons, for example, polyester, polyimides, and so forth. And beyond this group of thermoplastics, we have the next is the group of thermoset. And thermoset, the famous one, is epoxy. So the epoxy, for example, has relatively higher strength, but the modulus is very low because it's very rubbery-like material, so it can stretch quite a bit. So it gives you a wide range of properties in terms of strength, and modulus, hardness, elongation, and so forth for these types of materials. And as I mentioned, the composite materials, you use a combination of two or more dissimilar materials, and you can make them into particulate composite, randomly oriented short fiber composite, unidirectional composite, woven fabric composite, and all of these forms are usually in the form of laminates, of filler, to provide the stiffness, and is surrounded by a matrix. And this is a class of material that is very, very useful for many, many applications, including aerospace, as we will see that a lot of the new aircraft is made of composite. The skin of the wings and the body is made of composite materials because they are light weight and they have high stiffness. So this is going back to the polymers. We talked about this, and the elastomers are another class that is within the family of polymers, like polyurethane and butyl rubber and so forth. So rubbery materials are called elastomers in this case. Other materials are hybrids, like composites, foams, natural materials are hybrid materials, as you can see here. And then now, if we consider these families and we want to use them in a particular design, so the design will have certain specifications in terms of the Young's modulus, for example, that is required. Or the weight, or a combination of the weight and the stiffness that's represented by Young's modulus. So you would see just generally that the metals have the highest Young's modulus, from 100 to 1000 in units of GPa, and then below that you find that you have some of the lowest, at the lowest end of the Young's modulus, or the stiffness, is the titanium alloys, and then you get epoxies have reasonably low elastic modulus, in between 10 to 100, and then you get, if you want to use materials that stretch more or deflect more, then you will have to go down to woods and polyesters, and this range of materials have a modulus from 1 to 10. And if we want to have more stretchy materials, then we go down to the polymers, ABS, for example, and foams in here. And finally, if we just wanted to have very, very stretchable materials, for example, for applications in the new kind of electronics, like flexible screens, for example, then you have to develop materials that are flexible polymers that have very, very low elastic modulus. So let's discuss now how do we select materials? The material selection process is very interesting, and I'm going to outline it here. So the material selection depends on the loading conditions. And as you will see that the loading conditions determine what is required from the material. So let's consider a simple loading here where we have a tensile bar, and the tensile bar has a load P, and it has a cross-sectional area A, and the length is L. Okay, and then we stretch it. So when we stretch it, then the stress is equal to the force divided by the area, and we would like to it's an axial loading, very simple axial loading condition, and the axial loading condition that we have is we'd like to make sure that it is for minimum weight. So in the case of the axial loading, that it is minimum weight, then I'm going to minimize the weight, but I'd like to have it for large stiffness. So if I just do that, then I have essentially the stress is equal to the elastic modulus times the strain, and the strain is equal to delta L over L. So you have sigma is equal to P over A, or F over A, it's the same thing, is equal to E times delta L over L. And if we think of this material as a spring, then the load is equal to the spring stiffness times the delta L, and therefore I can just eliminate the delta L between these two, and I will have P over A is equal to E over L, and then I eliminate delta L. I write it as P over K, and that gives me that if P goes out of P, then I will have the property that the area, cross-sectional area, is equal to L over L times K over E. So this is what I got from here. Now I would like to minimize the weight, so the mass of the bar is equal to the density times the cross-sectional area times the length L. So if I write that down, be rho, and the area now is L K over E times L, and therefore I can separate this function into, which is the mass function, into a L squared times K times material property here, which is the density over the elastic modulus. So since L and K are either fixed or given by the design requirements, then the only material property that counts now is the combination of rho over E. So if I want to minimize the mass, then I must maximize the inverse of this. So I have to maximize the inverse of this, which is E over rho. So if you look at here, the mass is given by K times L squared times rho over E, and generally we can write the mass as a function 1 of the load times function 2 of the geometry, and we can fix those, and then the remaining part of this is a function of the material property, and it turned out to be rho over E, and therefore we maximize E over rho to select the material. So if I apply this on particular, now I have many classes of materials, so let's see how we can apply it on different classes of materials. We'll see that if we plot the Young's modulus as a function of the density, we can group the classes of materials together on that plot. So you will have the group of ceramics up here, you have the group of metallic alloys here, and you have the group of composites here, a family of composites here, and then we have a family of polymers here, and a family of elastomers, the rubbery materials, and then some family of natural materials, and then on the low end of this corner we have the foams. So it means that if we want now to maximize E over rho, we have a straight line that has the slope of E over rho, which is this straight line here, and I want it to be maximum, so I just raise the line along this direction until it becomes the maximum possible, which would be like something on this order like here, and therefore I discovered that I have to select a ceramic material like silicon carbide and silicon nitride. So that's kind of material selection without any other design constraint. So we will stop here, and we'll continue our discussion in the next segment.